For our first conformation, we want to write the Newman projection, and we want to show that the hydrogens are lined up directly behind the hydrogens on the front carbon. And typically how we can do that is to put a line very, very close to the one behind here. And we're supposed to interpret this as this hydrogen being directly behind the hydrogen in front. So these are connected to hydrogens. So we call this the eclipsed conformation. Like a solar eclipse or a lunar eclipse. The hydrogens in front eclipse our view of the hydrogens behind for ethane. So we like to identify the point group symmetry of this particular conformation. And the Newman projection works in a similar way to our six-pointed star representation for octahedral complexes and octahedral molecules, in that it makes it much easier to see threefold axes. So for example, along the carbon-carbon single bond, it's much easier to recognize when we have a C3 rotation. So for example, if we do a 120-degree rotation here, it's clear from the projection that this hydrogen will go to that hydrogen, this hydrogen will go to that hydrogen in front, and the same for the hydrogens behind. So it's clear that we really do have a C3 rotational axis. By the same token, we also have a C3 in the opposite direction, or C3 minus 1, for example. So for ethane derivatives, typically the high order rotation axis is going to be a C3, except in those cases we're going to see we might have something like a S6. But the highest proper rotation that we're likely to find in an ethane derivative is going to be C3, and we have that in the eclipsed conformation of ethane. Do we have any other symmetry elements here? Well, the one we want to look for is a C2 that is perpendicular to the high order rotation axis. We notice the high order rotation axis is along the dial here, so we might look for a C2, for example, along this line. So let's take a look at that along this particular axis and see what we get. Well, if we do that, we rotate along this line. The hydrogen in front replaces the hydrogen behind. They swap. The hydrogen in front here swaps with the hydrogen behind up there, and the same thing for the hydrogen in front here swaps with the hydrogen behind there. So that tells us that along this particular axis we have a C2 rotation. So we notice that we have at least one C2 that is perpendicular to our high order rotation axis. Since we have at least one, we know that there have to be three. So the other C2 axes will be along here. There's one. Rotate that way. And then we have along this axis here. So just because of that, we notice that since we have three C2s, so we have, they're perpendicular to our C3, which means that we have n C2s perpendicular to our Cn, we must have a D group. So it's got to be D3. And the important thing with ethane derivatives is often determining exactly which member of the D3 family to which a particular molecule belongs. So in this case, we need to look for the any possible mirrors. And we notice that the first mirror we always want to look for is the horizontal mirror. The horizontal mirror is the mirror that is perpendicular to the high order rotation axis. Our high order rotation axis here is a C3, so we're looking for a rotation in the plane of the board, reflection in the plane of the board. So that would be the whiteboard. And that would chop in between the two carbons of the ethane chain and reflect the top three hydrogens into the bottom three. We see that because we have an eclipse conformation, we actually have this situation. So we really do have a mirror in the plane of the board. So that tells us that we have the point group D3H if we have the eclipse conformation of ethane. So let's see if we have other conformations of ethane and to which point groups they will belong. So our second conformation will look like this. So here we notice that the hydrogens in the attached to the back carbon are exactly in between the hydrogens in front. So we call this the staggered conformation. So this is the staggered conformation of ethane. So we want to look for our high order rotation axis, and typically we're going to look for it along this particular axis here. So we notice that if we do a 120-degree rotation, that we line up hydrogen with hydrogen, hydrogen with hydrogen, and hydrogen with hydrogen. This tells us that we have a C3 proper rotation axis for this molecule. Now we also have another, in fact, a higher order rotation axis for this particular molecule. So let me just erase this and we can demonstrate where this improper rotation is going to take place. So we notice that if I rotate by 60 degrees here, this hydrogen will come to the same position as the hydrogen behind it, but it'll be in front. So it'll move this hydrogen to here, and then if I follow that by a reflection in the plane of the board, it will reflect a hydrogen in front to the hydrogen behind. And we notice that if I do this C6 plus a sigma H, that I line up the hydrogens, that tells me that I have an S6 high order rotation axis. I actually have an improper rotation. So that would be S6. So let's just confirm that that's going to be true everywhere else. I notice that for this hydrogen, if I rotate it by 60 degrees, it's going to be in front, then I reflect into the back. Same thing for this one if I rotate it by 60. Now, it's a little deceptive because my drawing isn't perfect here, but if I had drawn the angles perfectly to be exactly where they're supposed to be, we would notice that we have an S6 improper rotation for this particular molecule. The other thing about our high order proper rotation axis we noticed was the C3. So let me just notice what we have here. We have C3, we have S6. So then we want to look for any C2s that are going to be perpendicular to the high order improper or the high order proper rotation axis. If we look along, for example, the x-axis here, so we draw an axis here in the plane of the board, and then I do a reflection about this particular axis, I noticed it would take this hydrogen to that hydrogen. So these two hydrogens would swap. This hydrogen and that hydrogen would swap. This hydrogen and that hydrogen would swap. That tells me that along this axis I have a C2. So typically one of the places to look for C2s in Newman conformations is exactly halfway between a front hydrogen and a back hydrogen, or whatever the substituent there is going to be. So if I look along the bisector of that angle, that is a good spot to look for a C2. Do I have any other possible spots for C2s? Well, I have a possible C2 along here. And I notice that if I do a 180-degree rotation, it's going to take this hydrogen to that hydrogen, this hydrogen to that hydrogen, and this hydrogen to this hydrogen. This may not be obvious from a diagram, from a Newman projection diagram, so you should definitely try to convince yourself with molecular models that this really is doing what we say it's doing. And then last but not least, we have an axis along here. And this will take hydrogen to hydrogen, hydrogen to hydrogen, hydrogen to hydrogen. So we see that we have three C2s that are perpendicular to our C3. That tells us that we have a bunch of our three C2s. And I'm going to have the point group D3 of some type. So now the last thing to do is to look for mirrors. And we can recognize right away, because of this staggered conformation, that if I try to do a mirror in the plane of the board, a horizontal mirror, it doesn't exist, because that would reflect hydrogen in front to a hydrogen behind, which doesn't exist. But I do notice that if I look along a plane like this, it's going to reflect this hydrogen to that hydrogen. These two hydrogens are along the plane, so that's fine. And it's going to reflect this hydrogen and back to that hydrogen and back. So I see that I have what otherwise would be called a vertical mirror. In this case, just for historical reasons, we call it a dihedral mirror. So this gives us that, and we can find three of these just go along the hydrogen-carbon bonds here, and I would find the 3 dihedral mirrors. So that tells me for the staggered conformation of ethane, I have the point group D3D. Last but not least among ethane conformations, let's look at one last Newman projection. And this time we're going to put the other hydrogens not exactly lined up, but then again not exactly halfway in between either. So this is what we call a random conformation. And the key point is that the hydrogen in back is anywhere except exactly halfway in between the 2 hydrogens or exactly behind one. So take any other possible alignment, this is what we get. So again, we look for our high order rotation axis through the carbon-carbon single bond. And I do notice that if I attempt a 120 degree rotation from this hydrogen to that hydrogen, for example, that this works. So, and if I do it for the hydrogens behind, again, they're all set by 120 degrees from each other. So if I do a C3 rotation, they will line up. So C3 is again a symmetry operation of this particular group. So we have that. Let's see if we have any other interesting rotational axes, particularly C2s that are perpendicular to the high order rotation axis, which we notice is along this. Now, these are a little tricky to find, but as I said, I always recommend that we look for C2s exactly halfway between the front hydrogen and the back hydrogen. So if we look for a C2 along here, we notice that a C2 rotation would take the hydrogen in front to the hydrogen behind. It would take this hydrogen in back to this hydrogen in front and swap this hydrogen in front to that hydrogen behind, which is difficult to see from the Newman projection. Again, you want to build a model to confirm for yourself that this is true, but there will be a C2 there. Similarly, we can find a C2 that comes out along here. So that's a second C2. And then last but not least, we have a C2 that comes along this axis, comes out here. So we really do have 3 C2s that are perpendicular to our C3 for the random conformation. So there always will be these C2s for eclipsed, staggered, or random conformations of unsubstituted ethane. So therefore, we know that we must have, again, point group D3, or at least some member of the D3 family of point groups. But what do we want to look for now? We want to look for a mirror plane. If we look for a mirror plane in the plane of the board, it doesn't work because I notice that, for example, this hydrogen here doesn't have a hydrogen directly behind it that it reflects into. Then I want to look for something like a dihedral mirror, and I want to look for a mirror halfway between the hydrogens, the hydrogen in front and the hydrogen behind. And I notice that if I do this, there's a hydrogen here and a hydrogen there, but this one's in front, and it would get reflected to a hydrogen in front, not behind. So we don't have any dihedral mirrors. Since we have no dihedral mirrors and no horizontal mirrors, that tells us that we have no mirrors. So therefore, the final point group assignment for the random conformation of ethane is going to be D3. The next molecule that we want to look at is a monosubstituted ethane. So let's draw our Newman projection and look at essentially chloroethane here. From now on, in general, we're going to draw the staggered conformation because that's generally going to be the low energy conformation. So we want to look for our high order rotation axis, and typically we want to look down the carbon-carbon single bond. But we notice if I try to do a C3 here, it's going to take chlorine to hydrogen, so it doesn't work. We don't have a C3. And again, we don't have a C2 and those sort of things along that plane. But we might try some other axis. We might try this one, for example. So we might try along the y-axis, because it would take supposedly hydrogen into hydrogen. But really, if we did that, remember this rotational axis would have to be between the two carbon atoms. It would actually be in the plane of the whiteboard, so that this hydrogen, and the chlorine would be in front. So if we did a C2 rotation, it'd take this hydrogen to this position over here, but behind, not in front. So we don't have any C2s either. So it turns out we don't have any C2s, no C3s. The only symmetry operation that we're going to have is if we go along a plane here, I can also show as a metal ruler, that it reflects the left side of the molecule into the right side. So for our monosubstituted ethane, the only symmetry operation that we have other than the identity is the mirror. So that tells us that we have the point group CS. So let's take this particular situation and see if we can make it a little more interesting. And we can dye substitute our molecule. So now we're going to have a 1,2 dichloro ethane. 1,2 dichloroethane. There we go. And we're doing a particular conformation such that the chlorines are completely on opposite sides of the molecule to each other. So this is we call the anti-conformation. So here we have the anti-1,2 dichloroethane. So we want to look for symmetry operations. We look for a C3 along the carbon-carbon single bond. And again, for reasons we saw before, just because of the arrangement in the front group, chlorine, hydrogen, hydrogen, that a rotation would take chlorine into hydrogen, so we do not have a C3. But we do have a C2, and it's an interesting place, which we may not have immediately noticed. That if I look at an axis along here, along the x-axis, so I can put my dowel to show this, that if I do a C2 rotation, it's going to take the chlorine in back to the chlorine in front. It's going to take the hydrogen in the front to the hydrogen in back. So I actually have a C2. It's kind of a location I might not have expected, but we have a C2. So a high order rotation axis for this anti-1,2 dichloroethane is a C2. Do we have any other interesting symmetry operations? Well, we notice that, like the previous molecule, we have a mirror plane that goes along here. You have a mirror plane along that way. I'll just highlight that in orange here. Here's where the mirror plane is going to be. It reflects the left side of the molecule and the right side. So we notice that we have, and this mirror plane is actually going to be, see if I can demonstrate this, our mirror plane is actually perpendicular to our high order rotation axis. That tells us that our mirror is going to be a horizontal mirror. So that means that this is going to belong to the point group C2H. And as we recall, one of the interesting things about C2H is it's a centrosymmetric point group, so that we must also have inversion here. And we notice that it's hard to draw in this representation, but if I drew a line from the center of the molecule, which would be halfway between the two carbons, to this chlorine atom, the vector would of the same length in the opposite direction would reach this chlorine. And the same for this hydrogen is the inverse of this hydrogen is the inverse of that one. So this molecule exhibits all four of the symmetry operations of the point group C2H. So now that we've seen the anti-conformation, let's show one other conformation of the 1,2 dichloroethane. And in that case, we're going to put the chlorine in back in this position. Now we have chlorine here as opposed to there. And what we want to do is determine the point group symmetry of this particular molecule. If I look for the C2 in the previous location, I see this will not work because rotation around this axis would take chlorine into hydrogen. It doesn't work. This one is somewhat challenging to find the symmetry operations for. And again, if we don't see a C3 in the same axis as the carbon-carbon single bond, typically we want to look for is a C2 axis that goes between atoms. So if it goes between the hydrogens here and the chlorines here, I notice that if I do a C2 about this axis, it's going to take chlorine to chlorine. This hydrogen goes to that hydrogen, and this hydrogen and that hydrogen are swapped. So I have a C2 axis for this particular conformation, which we call the Gauche conformation. So this is the Gauche. The Gauche conformation for the 1,2-dichloroethane. And then we want to look for mirrors. And we notice something, it's kind of interesting, is that there's no horizontal mirror. There are no vertical mirrors. So we don't have any mirrors at all for this particular molecule. There's no inversion. There's no improper rotation axis. The only non-trivial symmetry element that we have is the C2. So therefore, this molecule belongs to the point group C2. Perhaps we should look at the tri-substituted ethanes. So let's look at one such substitution pattern. And that is if we put, let's do fluorine this time, 3 fluorines all on the first carbon. So I have the 1,1,1 trifluoroethane. So I want to figure out what the point group symmetry of this molecule is. As we've been doing, we often look along this particular axis to look for the high order rotation axis because we found C3s there before, and we notice we have another C3. So rotate by a C3, it's going to take the fluorines into the fluorines, and the hydrogens behind the plane are going to be taken into each other. So this molecule actually does have a high order rotation axis, which is a C3. Next, we wanted to look for C2s, but I would look for C2s in any of the places I might have normally found them before. Any C2 rotation in these kind of directions would take the fluorines in front to the back, and I know that in the back I only have hydrogen atoms, so there's no C2s that are going to be perpendicular to our C3. That means we don't have a D group. Maybe we might have mirrors, so let's see if we have any mirror planes. And I notice that if I look along this plane here, it's going to reflect the left half of the molecule into the right. So I actually have a mirror there. I have a mirror along here, and I have a third mirror here. And because these mirrors include the high order rotation axis, and I can demonstrate that, here is the mirror plane, here's the high order rotation axis. We see it's actually in the same plane. That tells us that these are vertical mirrors. Therefore, this molecule belongs to the point group C3Z. Now for another combination, let's remove one of the fluorines and see what happens to our point group symmetry. So notice, in comparison with some previous examples, previously we had chlorine on both carbons 1 and 2. Here the fluorine substituents are both on the first carbon. So we have a 1,1-difluoroethane, and we want to ascertain the point group symmetry of this particular molecule. So again, we look along this axis, but it would take hydrogen and a fluorine. It doesn't work. So we don't have a C3. Maybe I look for C2s, and kind of notice that I have 2 fluorines here. Maybe I'll try a C2 along the y-axis. But if that were true, it would take this fluorine into a fluorine behind a plane, not in front of it. So there's no C2 there. Similarly, if we try any of the other likely positions for a C2, there are none. So we notice that the high order rotation axis for this particular molecule is only C1, the identity. But we do notice, kind of comparing to the previous molecule that we looked at, if I check along this particular plane, I notice that it really is a mirror plane. So we actually have a mirror plane in the YZ. So we actually have a YZ mirror here. But that's the only mirror that is possessed by this entire molecule. So that tells us that the 1,1-difluoroethane has point group symmetry CS. The next molecule we'd like to look at has 4 substituents. So we can draw the Newman projection. In this case, And we have 4 chlorine substituents, in addition to the 2 hydrogens that would normally be there. So here we have the molecule 1122 tetrachloroethylene. So we want to look for the symmetry operations of this molecule. If we look along this particular axis, the carbon-carbon axis, we notice that if we try to do a C3, it would take hydrogen to chlorine, so there is no such axis. And in this particular plane, we have no high-order rotation axis greater than a C1, so we don't have that. But let's see if we have any other interesting symmetry operations, particularly C2s elsewhere. So let's look along the x-axis and see if we can find a C2 rotation here. If there were, it would go along this particular axis. And we notice that if there are such a C2 here, it would take chlorine in front to chlorine in back, chlorine in front to chlorine in back, and hydrogen in front. Hydrogen in back, hydrogen in front, hydrogen in back. So we actually do have a C2 axis along here. So we do have a C2 axis. Do we have any other C2s that we can find? Well, if we kind of look along here, it would take chlorine into hydrogen, for example. We might try along here, but then it would take chlorine to hydrogen, so we don't have any other C2s. We just have one C2, so our T2 is going to be our high-order rotation axis. Next, we want to look for mirrors. One typical spot we might look for a mirror would be in the plane of the board, but that would reflect a chlorine in front to a chlorine behind, and there is no chlorine there. So we don't have a mirror in the plane of the board. We do have a mirror that goes vertically like this, so we can denote that line along here in orange. That's our mirror. And if we use the ruler to show it as a plane, we see this is the YZ plane, and it reflects the left half of the molecule into the right. So we do have a mirror plane. And we notice something interesting about the mirror plane is that the mirror plane is normal to the high-order rotation axis. That tells us that our mirror plane is a horizontal mirror. So since we have a horizontal mirror and a C2 axis, we realize that we have the point group C2H. We also recognize that if we have the point group C2H, it's not required to classify the molecule, but we know has to be there as part of the group, the inversion operation. And we notice that if we go in this particular direction to chlorine, I go in the opposite direction, the same amount, same distance, I will also reach a chlorine. For each and every atom, if I go in one particular direction, if I go to the opposite side of the molecule, I see the identical type of atom. So it does show that I have the inversion operation. Therefore, this molecule has the property of being centrosymmetric. Let's try to change up the substitution pattern and see what we get. So in this case, we're going to have chlorine here, chlorine there. We can put iodine here, iodine there, and the other positions we're going to have bromine. So we have a 1,2-dibromo, 1,2-dichloro, 1,2-diiodoethane here. And we want to determine the point group symmetry of this molecule, which looks kind of complicated. Since we see these pairs of atoms of the identical elements, one of the first things we might look for is some sort of a mirror. So I might look for a mirror in the plane of the board. And the mere fact that we have a staggered conformation tells us that we can't have a mirror plane in the plane of the board. perhaps we might have some sort of a mirror like this, some sort of a vertical mirror. Now this looks like it might work, except I realize that this iodine here is in front of the board. This one is behind the board. So a reflected here would reflect it to an iodine that was also in front of the board. So therefore, no matter how we try to arrange for a vertical mirror, there is no such mirror. But we still recognize these pairs of elements. We might want to try something else. Let's try along this particular axis. Let's look for a possible C2 axis. So let me draw where this might be. So if we try along this line here, so it's going to be, if we were drawing it with precision, it would be exactly halfway between this bromine and that bromine, between this iodine and that iodine. And we notice that if I do a C2 about that axis, which would be about this axis, it would take the iodine in front to the iodine behind. It would take this chlorine behind to a chlorine in front, and would take the bromine in front to the bromine behind. So those would get swapped, the chlorines would swap, and the iodines would swap, which shows us that we really do have a C2 axis, a C2 rotation about this axis. And other than the identity, this is the only symmetry operation of our molecule. Therefore, now, just one other thing we might want to check is, oh, well, maybe we have inversion, because I notice that if I go in this direction, from the center of the molecule to chlorine, I also go the identical distance here, I do reach a chlorine. So the chlorines at least seem to fulfill an inversion operation. But if I go in this direction to bromine, I go the opposite distance, I reach iodine, which is not the same element. So therefore, while it works for the chlorines, it doesn't work for the other elements in the molecule. Therefore, we do not have inversion. And the proper symmetry assignment for this molecule is going to be C2. Let's try just one more substitution pattern of a substituted ethane, and see if we can assign its point group symmetry. So in this case, we're going to have, again, we're going to put the chlorine atoms like so, but now we want to put iodine here, and then bromines at the remaining positions. So again, we notice that we have a 1,2-dibromo, 1,2-dichloro, 1,2-diiodoethane, even though the actual arrangement of the atoms is somewhat different here. So let's see what we have in this particular case. And we look for what symmetry operations this thing has. And the only one that we notice, if we look long enough, we could try for C2s, C3s, and mirror planes. But the only symmetry operation that's going to be here is, we notice if we go a certain distance to chlorine, and I go the equivalent distance in the opposite direction, I reach a chlorine. If I go in this particular direction to bromine, and then I go in the opposite direction, I also encounter bromine. And if I do it for the iodine, I go a specific distance. I go the same distance in the opposite direction, and I reach iodine. So the only non-trivial symmetry operation that this molecule possesses is the inversion. When we just have the identity and the inversion, this belongs to the group Ci. So I thank you very much for your attention. Don't forget to subscribe to my channel. Have a good one. Subscribe to my channel. Have a good one.